Hello everyone, I'm Vaibhav Gupta, and in this video we'll go over some different types of quantum computers, and we will also understand some basic computational mechanics, and then we'll see which companies are at the forefront in this space. So let's get started. First one are the types of the quantum computers. Currently the quantum computers are categorized into three different types. The first one is quantum annealing. And these are the most restrictive form of the quantum computers, and these are best if we want to solve one specific function or one specific problem. These are easiest to build. A company like D-Wave have implemented the quantum annealing computers, and here right now these are best for solving the optimization problems. As what these computers does is it takes all the possible wave states of the wave function, and it collapses into one state which has the lowest energy or the entropy. The second one are the simulation quantum computing or the analog quantum computers. They have the generality, or they have the partial generality, and these are best for simulating the quantum interactions that we cannot simulate using the classical computing. That's why they perform best when we have to do chemical simulations, or we want to do some biological system simulations like simulations of proteins or biomaterials. The third one are the grand challenge in the quantum computing space. These are called the universal quantum computers. They are the general purpose quantum computers, and they can give us the exponential speed increase over the classical computers. They are the most hard to build, and the companies are researching into building these universal quantum computers. Current estimates indicate that these computers will have more than 100,000 physical qubits. So this was about the quantum computers. Let's understand the basic computation mechanics that's there in the quantum computing space. Similar to what we have in the classical computing, these quantum computations also have gates. Like the first one, which is gate X, which is a Pauli operator. Just before that, as we remember from the previous videos, that I can define my wave function as this, where 0 and 1 are my orthogonal bases, right? So if I have to draw the diagram of this, it will look like it's at 0, it's at 1. And I can denote my 0 as 1, 0 matrix and 1 as 0, 1. So what gate X does is it flips the bit. So if my wave function has 0, the state of 0, it will flip it to 1. If that's 1, it will flip it to 0. The second one that we are going to discuss is the Hadamard transform. It's a very important transform. What it does is it transforms your state by pi by 4, by the phase of pi by 4 or 45 degrees. So let's say change the color, let's say my initial state was at 0. It will change it to pi by 4 till here. So this will become 1 by root 2, 0 plus 1. And this is what we say as plus 1. So this will transform my 0 state to the plus state, or the 1 by root 2 into 0 plus 1. The third one is the C naught or the control naught gate. It is, I believe it is one of the most important gate in the quantum computing. So what it does is it takes one qubit as the control input, and it changes the state of the another qubit depending on the state of the first qubit. So if this state has 0, this qubit has the state of 0, then it will not change the state of this qubit. So if it's 0, it will be 0, sorry, or if it's 1, it will be 1. But if this qubit state is 1, then it will flip the state of the next of the second qubit. So if it was 0, then it will change to 1. If it was 1, then it will change to 0. There are many more gates in the quantum computing. So I just discussed three to give the basic understanding of how the computation mechanics works in the quantum computing world. Now let's see if I want to develop a simple algorithm. So here what we do is we define the circuit and so that we can get the favorable outcomes. So let's try to build an entangled state or the Bell state. Sorry for that. So we'll try to simulate a Bell state, which is an entangled state. So let's say I have two qubits and I have reset them to 0. I can put a Hadamard transform on the first qubit. If I put a Hadamard, it will give me 1 by root 2 plus 1 as an output. And then I will use this as a control input for my second qubit. So now this goes as a input to this qubit, which started at 0, or it can start at 1. So after I give, and this is a CNOT gate. So this gives me the output as 1 by root 2, 0 plus 1. And as we know, and it is same as this function, this wave function. So as we know, this is an entangled state where if my first my first qubit is 0, then the state of my second qubit will be 0. And if my first qubit is 1, my second qubit will be 1. There will not be any, the probability of first being 0 and the second being 1 is 0. And the probability that my first qubit is 1 and my second qubit is 0 is also 0. So only these two states will exist, and that's how these are entangled. Now I can say that my first qubit and my A1 and A2 are entangled. So this is how we can implement the algorithms, and we can use different gates to implement more complex algorithms in the quantum computing. So this is about the mechanics. Now let's see which companies are at the forefront in this space. So first, which is the most famous one, is the IBM Q system. They are using superconducting material as their qubit, and they currently have around 20 qubit system. The second one is the Rigetti. They are also using the superconducting material as their qubit, and their system is around 28 qubits. And then we have the D-Wave. They are using the quantum annealing as a quantum annealing computing system, and they have around 20,000 qubits. So we can solve the optimization problems using the D-Wave. And if we talk about the upcoming quantum computers, the Zenodo is upcoming with a photonic qubit quantum computer. The IonQ is implementing a trapped ion qubit quantum computers. So this is all this in this video. In the next video, we'll go over some real world applications of the quantum computing algorithms. So thank you for now, and I'll see you in the next video.